Okay, so this is our last PowerPoint on vectors in 3 dimensions, and the topic mostly is going to talk about the cross product and how we can apply the cross product to solve some problems. What's an example? Find a unit vector that is orthogonal to both A and B. So if you'll recall that orthogonal just means perpendicular, so that means we need to find the cross product between A and B. And I'm going to forego the details by now. I think you probably know how to do this, but the cross product here for this would be negative 3i plus 2j plus 11k. Now what we want is this to be a unit vector. So remember, to make it a unit vector, we just need to find the magnitude of this new cross product. So the magnitude of this vector gives us square root of 134. So a unit vector that's in the direction of A cross B, we would just take our A cross B vector and we would times it by 1 over the square root of 134. So another formula that is used very often is to find the magnitude of a cross product. And this formula is in your info booklet, so you don't have to worry too much about memorizing it, but just know that it's there if you need it. So if I wanted to find the magnitude of A cross B without actually going to the trouble of finding the cross product, it would just be the magnitude of A times the magnitude of B times the sine of the angle between them. An application that IB is really fond of is finding the area of a parallelogram by using the cross product. The area of a parallelogram is just the magnitude of its cross product, where A and B are adjacent sides, or vectors representing the adjacent sides of the parallelogram. Let's do a quick example here. Show that the quadrilateral with these vertices at the following points is a parallelogram and find its area. So here's a little picture of it. You don't have to worry about trying to draw this in 3 dimensions. You could just draw it in 2 dimensions if you want to, like we were doing last week, even though it's 3 variables. But remember, you want everything to go in order. So the way they drew this one is they've got A at the bottom, followed by B, then C, then D. So remember how we're going to look at this. We need to find vector AB. And so AB is just the vector negative 3i plus 4j plus k. And then since we want to go in the same direction as AB, we need to find BC. So how does that show that that's a parallelogram? If AB is equal to BC, remember the vectors are same length and same direction because they're equal, so therefore this is a parallelogram. Now to go ahead and find its area, we need to find the magnitude of the cross product of 2 adjacent vectors. We could say that AB is adjacent to, say, BC. We could have used AD as well, that would have been fine. So BC is negative 2j plus 6k. Now we don't know the angle between them, so we're going to just go ahead and have to find the cross product and then take its magnitude. The cross product, using our formula from last week, and if you work that out, you should get 26i plus 18j plus 6k. The area of the parallelogram is just going to be the magnitude of that cross product. Square root of 26 squared plus 18 squared plus 6 squared would get you 1036. Of course, you can leave it as a radical or a decimal. Another application of cross product is to find the area of a triangle, and we would do it very similar to how we would have done it in geometry. Area of a parallelogram would be base times height. The triangle, of course, would be half of that. And so the idea is the same with vectors. If the area of the parallelogram was the magnitude of the cross product from A to B, then the area of a triangle would just be 1/2 of that. One thing to keep in mind, and it was the same when you did the parallelogram a second ago, that the vectors have to be adjacent. They have to emanate from the same point when you're working with your triangle. Let's take a look. If it says find the area of triangle ABC and you're given points for A, B, and C, we're going to need to find two vectors that come from the same point. So I found vector AB and AC. Now you could have done BA and BC or CA and CB. Doesn't matter, just make sure they emanate from the same point. We're going to find the cross product of AB and AC. And I get a cross product of I plus 13J plus 10K. Find the area of our triangle, we're going to do 1/2 of the magnitude of that cross product. That gives me 1/2 of the square root of 270. Okay, next application of the cross product is something called the triple scalar product. And the notation for it is A dot B cross C. So we need to find the cross product between two vectors B and C first. And then we're going to do the dot product with that cross product and vector A. And a quick way of doing that is to just do the determinants of A1, A2, A3, B1, B2, B3, and C1, C2, C3. So we're dealing with three vectors here. So think about it, your final answer here is going to be a number. So this is primarily used for, and by the way, I want to point out that this formula I don't think is in your info booklet. So this is one you're going to want to make sure you have memorized. But it's pretty easy to remember. Just know that you put the three components of the three vectors into the determinant. This is used to find the volume of a parallelepiped. I love that word. I think that's an IB word. Never heard it before, but it's just a three-dimensional figure, parallelogram-based prism. The volume of this figure is the absolute value of that triple scalar product. Now I'm saying absolute value because remember that triple scalar product was a number. It was a determinant of a matrix. So if that number happens to be negative, it's just going to make it positive. So again, we're talking about a three-dimensional figure. We're talking about three vectors that all come from the same point. So we've got vector A, vector B, vector C, representing these three edges. I've got a little proof here of where this formula comes from. It's not terribly difficult to see where it comes from. What they did is they did the base is a parallelogram. So to get the area, that would be the magnitude of the cross product of the area of this parallelogram. Well, that would just be two adjacent sides, so that would be B and C. And I've got a little picture here. Here's a little application of projection vector. So if this is vector A, remember this is vector B cross C, and that's perpendicular to the base that contains B and C. So the projection of A onto the cross product for BC, that would be the projection of A onto B cross C. So this distance from here to here is the height of the parallelepiped. So the height is given by the length of that projection vector. If you remember from geometry, if you have a three-dimensional figure, the volume is the base area times the height. That's just your projection vector times the magnitude of that cross product. You recall how we do projection vectors. It's the dot product of those two vectors divided by the magnitude of that cross product. And then since we're multiplying that by B cross C, the magnitude of B cross C here, those would divide out. That's where the formula for the volume of this parallelepiped comes from. Okay, so let's do one. It's really a pretty easy formula to use. So find the volume of the parallelepiped having these three vectors as adjacent edges. Got a nice little picture here. Don't worry about trying to sketch it. It's pretty complicated. I'm not good at drawing in 3D, so don't worry about drawing it. They told you these are adjacent vectors, so we're good to go. We can just put this into our triple scalar product formula. So 3, negative 5, 1, 0, 2, negative 2, and 3, 1, 1. Remember, there's no IJK in that first row, so the result of this is going to be a number. This is a true determinant, not another vector. So if we use our determinant formula from matrices, and you just expand that first row, 3, negative of the negative 5, and then 1, get a value of 36. And again, if this had been negative, you just make it positive. It's the absolute value of that triple scalar product. Okay, last application we're going to look at is how to test to see if points are collinear. I'm sorry, mess that up. If points are coplanar this time. So we're looking at 4 points and we want to know if they're in the same plane or if they're in different planes. If you're given 4 points in space, there are two possibilities. Either they're on different planes and form a tetrahedron, that's a four-sided figure, or they're in the same plane and they're collinear. So 4 points, A, B, C, and D, that have position vectors A, B, C, D are coplanar if and only if this is true. Now, this looks a little complicated, but this really is just the triple scalar product, where the vectors you're looking at are B minus A, C minus A, and D minus A. And if that equals 0, then the points are coplanar. This formula, by the way, is not in your info booklet either. It's another one you need to memorize. Okay, so here's an example. So we have these 4 points. We want to know if they're coplanar. So I'm going to look at B minus A, C minus A, B minus A. Then we're going to put those together and do the triple scalar product of these 3 vectors that we just came up with. And if we go ahead and work out the determinant, I'll spare you the details, but the determinant here turns out to be 0. So that tells us that these are coplanar. If that determinant had been any other number, then they would have been not coplanar. So this is a pretty easy test to look at. Okay, and that's the last part of vectors and applications of the cross product.